Okay, here is our reaction from yesterday. We had the almost colorless N2O4 turning into nitrogen dioxide and vice versa, right? They're both gases. So in order to figure out all this equilibrium constant stuff that we are talking about in this video today, we first just need to think about this in context of what the different reactions are and what's going on there. So let's just try first. Can you write out just the forward reaction? Okay, go ahead and do it. Okay, so N2O4 becomes 2NO2. Okay, let's write the reverse reaction. Great. Okay, now can we write the rate laws for these two reactions, assuming they're elementary? Okay, let's do it. So first of all, every rate law, rate equals K, and we're going to call this KF, K forward, okay, K, and then what is it dependent upon? It's dependent upon those reactants, right? Concentration of N2O4, first order, right, if it's elementary. Let's write the rate law for the reverse reaction. So rate is going to equal K reverse of NO2, and then that's going to be second order. Okay, great. So we have these set up. Now, what we talked about yesterday for equilibrium. Equilibrium means that the rate of the forward reaction equals the rate of the reverse reaction. So these things are equivalent, which means these things equal each other. Okay, so let's just write that out. So KF multiplied by N2O4, concentration of, is going to be equal to KR NO2 to the second power. Okay. Whew. Now, let's rearrange this. Can you get the constants on the same side and everything else on the same side? I think we can. So here's what we're going to get. NO2 to the second power over N2O4 is going to be equal to KF over KR. What do we do when we have two constants on the same side dealing with each other? We just call those K. In this case, we're going to call them Kc because it's based on concentration, and this is called the equilibrium constant. That is the name for this. So notice what we have. We have concentration of products to the power of their coefficient over the concentration of the reactants, and that is equal to a constant. Okay, it's called the equilibrium constant. Let's look at the equilibrium constant for something called the Haber process. The Haber process was discovered by a man named Fritz Haber, who was not great. I'll post a video. Not a great dude. But this is what feeds most of the world. This is a very common reaction that we see in the AP exam. This is a good one to be familiar with. You've seen it a few times in class, okay? So these are all gases. And what did we figure out? When people were studying equilibrium in the 1700s and 1800s, what they figured out was that anytime you had this relationship of the products to their stoichiometric power over the reactants to their stoichiometric power, there was a constant that was the same, no matter how much of each thing you started with. Did not matter. They always had the same relationship, okay? This is something called the law of mass action. Okay, and so we're thinking about this as like activity and action. So let's just see what we can do as we figure out what that law of mass action means. Okay, so here's what it is. We have some products, and this is just our totally generic equation. We have some products, they have a stoichiometric coefficient out front in equilibrium with their products, which also have a stoichiometric coefficient out front, and this is how we set it up. Kc is always equal to the concentration of the products raised to their coefficient over the concentration of the reactants raised to their individual coefficients, okay? So this is something you just need to know how to do. It is on your green sheet. So let's try and write up, this is called an equilibrium constant expression. Let's write it for the Haber process, but let's do it up here. Okay, so it's going to be Kc, and then up top, we put products, right? So we're gonna put NH3, concentration of NH3. There are no 2's out here, okay? That's not where they go. It goes up here. Okay, so there's our product over our reactants. So we have concentration of N2 and concentration of H2 to the third. Okay, some things you need to do. If you're writing Kc, you have to have brackets to show that this is concentration. You have to raise them to the power of their coefficients. Okay, so there we go. That's the answer. So let's practice a few. I want you to go ahead and see what you can do with this problem. 2O3 becoming 3O2. Give it a shot. Okay, I hope that's what you got. Now let's try B. So there are our answers. So you can see products raised to their coefficient power, reactants raised to their coefficient power, same thing here, all to the first, and the second. Okay, so how do we actually get a number for Kc? Because that is a numerical constant value. So let's just try it. Let's go back to this N2O4 to NO2 equation. And what you're going to get is you'll get data. So maybe some sort of at equilibrium, these are your concentrations. So what I'm giving us in this problem is we experimentally measured at equilibrium. So when everything settled down and their concentrations quit changing, we had this much NO2 in terms of molarity, this much N2O4 in terms of molarity. Let's calculate Kc. So first we need an expression, right? So let's go ahead and write that expression. Kc is going to equal NO2 N2O4. Okay, and now we know these concentrations. So we're just going to take this, plug it in there, take this, plug it in there. Go ahead and get a number. Make sure to square it. Okay, so when great. Okay, so when I plug these numbers in, the number I got for Kc was 0.211. So that is the value for Kc here. All right, can we also do this with pressure? Yes, and the AP exam is going to ask you to do this. We have to be really careful about labeling, right? So notice how much different this is. No more brackets, and what we do is we write a big P to show we're talking about pressure, and then you always write the formula down here as a subscript for the pressure. Again, it's still raised to the power, so almost nothing has changed. We label Kp, we make sure we're using pressure. So let's write this same equation, but let's write this equilibrium constant expression in terms of Kp. Okay, I'm gonna bust out my marker for this. Okay, so we're gonna write Kp for ourselves, okay? And what are the products? NO2. So it's the pressure of NO2 to the second over the pressure of our N2O4. Okay, and that's how you list that out. All right, can we convert between these two things? Let's see if we can go between these two. I'm going to drive this just really quickly, and you won't have to do this on the exam, but it is going to be important for you to just know where it comes from, how to use the equation at the end. So how do we go between concentration and pressure? Well, we have our old ideal gas law that we know and love. If we rearranged it in terms of pressure, I want you to notice right here, this is moles over volume. That's concentration right there. So that makes things pretty nice for us. So how can we do this? Okay, well, let's just assume we're talking about a generic thing A, okay? generic reactant. How about? Okay, so the pressure of A is going to be equal to the moles of A over volume times RT. Okay, so I just started using A here. How else we can write this is, let's just combine these terms right here and call it concentration of A, RT. I hope that's okay with everybody. Again, you aren't going to have to do this on your own. Okay. So now what we're going to get is the pressure is going to be equal to this amount here. Okay, so if I wanted to try and write an equilibrium expression in terms of pressure, what I would do is generically it would look like this. The concentration of D times RT, okay? We getting where this is coming from? And then that would be multiplied by the concentration of E, and then raised to the power of D, concentration of E, RT, raised to the power of E, okay, over the concentration of A, RT, to the power of its coefficient, B, RT, to the power of B. Holy mackerel. Okay, so now we have a lot of stuff going on here, right? So let's just pull some of this out. Let me change my color to green. So if we pull this, and this out, right, with their coefficients, we get KC, okay? And then we have RT here. So we're going to have RT, and then this is all going to be raised to the power of D plus E, okay, minus A plus B, just because of the relationship here. So what we have is KP is equal to KC times RT to this power. What we can do here, this is the number of moles of products, right? And this is the number of moles of reactants. So we're going to simplify this and just call it delta N, okay? So what delta N equals is moles of product minus the moles of reactant. Okay, so that'll be delta N. So that's how we get between the two. Holy mackerel, let's try it. Okay, so we're back to our Haber process. Okay, they're giving us Kc. The value is 9.60. It's at 300 degrees C. We just need to know that and say it's consistent. We're then going to calculate Kp. So I gave you the equation right here. So let's just start plugging things in. So what's Kp? Kc is 9.60. What is R? R is our ideal gas, right? And let's figure out the units for that. We're not sure. So what is this? This is in Celsius. Then we're going to have delta C up here. Okay, so for our value of this here, so it's going to be 0.8206, okay, is our usual value, okay, and liters, moles, atmospheres, yeah, and then we are going to multiply that by 573K. That's our Kelvin. Let's make that a real capital K. And then this is to the value of change in moles. So how many moles of product do we have? 2 moles, right? How many moles of reactant do we have? 4. So 2 minus 4 is -2. Okay, so we did that problem there. Let's calculate it. Go ahead and get a number. Okay, so I got that it is going to be equal to 4.34 times 10 to the -3rd. You might be thinking, okay, Miss Brown, these units seem whack. What is going on here? There are no units. There are no units of Kc and Kp. I'm sorry. There's something called activity, so they explain like how active a reaction is, and as we get further into equilibrium, we'll talk about them, but you kind of get to ignore your units here. Just make sure if you're calculating Kc, you're using concentration. If you're calculating Kp, you're using pressure. You can never just use moles. You have to use molarity, or you have to use partial pressure, okay? All right, last part of this, if you're going to mix up some states, okay? If we have different things, so far we've had only gas stuff or only aqueous stuff. Here we have a problem with some solid lead 2 chloride becoming lead 2 ions and chloride ions. What does the equilibrium depend on? So I made a little picture here. So we have this solid, and then we have all this stuff bouncing back and forth. And according to our collision theory, reactions happen when things collide, right? So this solid isn't really colliding that much. So we are going to not take it into account in our equilibrium expression. So when we write this out, it's only going to depend on the concentration of our 2+ ions and our chloride ions. Okay, and don't forget, I need to have that 2 up there as the exponent. Okay, how's that going for people? I hope that's all right. So what do we need to know? Whenever a pure solid or liquid is involved in a heterogeneous equilibrium system, we don't include it in the equilibrium constant expression. Okay, last page. So let's just try and write this out for a couple things. Let's write out Kc and Kp for this one. Okay, so we have some calcium carbonate becoming calcium oxide and carbon dioxide gas. So Kc is going to be equal to, well, we're going to ignore this solid, we're going to ignore that solid, so it looks like it's just dependent upon the concentration of CO2 to the first power. Okay, let's write Kp. Kp is going to be equal to the pressure of CO2. Full stop. Not too shabby, huh? Let's try this one. We have liquid water and some carbonate ions, and then we have hydroxide ions and bicarbonate. Let's write Kc. All right, so Kc is going to be equal to the products, concentration of cool. So at the end of this, what did we learn? Well, hopefully we know that equilibrium is predictable and the relationship of the reactants and products is constant. Okay, you should be able to write an equilibrium constant expression in terms of concentration or pressure. You should be able to convert between Kc and Kp, and you should know what to do, how to write an equilibrium constant expression when the equilibrium is heterogeneous. Nice job.